This is Lab 5, the physics of fountains. In this lab we will compare the motion of a projectile with the motion of a jet of water in order to find out more about the mechanics of a fluid in a fountain. We can look at what is different in the motion to see what is different in the underlying processes. We find that there are unseen forces acting on the water while still in the air. In particular, more than gravity is affecting our system. To prove this, we first need to quantify our motion using tracker, create a model using the initializing data from that motion, and compare the results. Once we've done that, we can start thinking about why the motion changed, what's different in the system that caused us to observe different motion. This video came from Centennial Olympic Park, so it's quite busy, and my girlfriend's there for scale. So first off, some differences between projectiles and the jet of water are obvious. The water isn't cohesive, so when it encounters air resistance, it breaks up. The result is that there is no clearly trackable feature. So a bit of the tracking here is guesswork, but we still end up with some useful data, even if it isn't quite exact. So why compare a simple projectile to this complex motion? Because if the data does change between the two systems, then we know something's fundamentally different. Newton's second law lets us know that a change in motion tells us something about the net force on the object. If the entire net force is the gravitational force, then we'll see one set of motion. If the net force is the gravitational force plus some other sort of force, then we'll see different motion. That means if we do see different motion between these two, we can know something about this question mark force. Tracking water is less straightforward than tracking an object, so multiple tracks are applied to get as many useful points of comparison as possible. Track A watches the jet as it moves up. Track B follows the end of the jet, and Track C observes the water as it falls. Our analog model is a ball being launched up at an initial velocity and falling back down. It is initialized by the initial position and velocity of the jet of water. While the ball is above its initial position and velocity are updated by Newton's second law. I have also programmed in a command to print the time and height when the ball is at its maximum height, where the velocity becomes close to zero. This outputs an easy-to-read sentence like this. Now that we have both sets of data, we can compare them, and as you can tell, the differences are striking. The model reaches a much lower maximum height than our initial tracks. Recall that track A is a track of the jet just beginning to shoot out of the spigot, and track B is following the tail at the end of the spout. We can factor out this discrepancy being because I didn't include drag in the model, because if I did include drag, it would reach an even lower height because its speeds would be diminished. So that's not really a major factor. So what is it that causes this actual height to be so much higher than this maximum? Why does it take so much longer to attain it? The data suggests that there must be a significant upward force being applied to the water at the crest in midair. The initial velocity the jet started out with just didn't give it the kinetic energy to reach the height that it eventually did. That extra height must be given by higher velocity water coming down and pushing the initial water up. Strictly by observing motion, we've been able to deduce something about the pressure in the nozzle. This makes sense because we see track B has a much higher velocity than track A. This is because track B was seen at the very end of the spout. That high pressure and thus high velocity had already been reached, whereas for track A, the spout was just starting, and so the pressure and velocity had to build. We can also use our data and the energy principle to estimate the maximum height based on the initial velocity plugged into our model. And indeed, this is the maximum height that our code outputted. If we flip the equation around, we can figure out what the initial velocity was needed for the actual water to reach the height it did. So following this calculation, we know that the water had to be moving at about 6.5 meters a second at some point during the jet to be able to reach 2.15 meters in the air. In conclusion, based on the differences between the observed motion and the projectile motion, we're able to infer the jet had non-constant pressure, meaning it changed from low to high pressure, during the course of the video, and we were able to figure out actually what velocity the high pressure water was coming at to make it achieve the height of about 2.5 meters.